All right, welcome to Chapter 20, Thermochemistry, podcast number 5. This podcast is going to basically talk mostly about the reaction quotient, right, which is also going to help us figure out which direction our reaction's going when we're not at equilibria, right? Remember that that's going to tie into, right, when we are driving our reactions towards equilibria, it's going to be spontaneous. If we're driving it away from it, it's non-spontaneous. So we're going to revisit our reaction quotients. So here we have the reaction of solid zinc plus two strong acids are producing zinc 2 and a hydrogen gas, right? H2 gas. Remember that when we do a reaction quotient, just like an equilibrium constant, gases are their partial pressures, aqueous things are their molar concentrations, moles per liters, and we exclude liquids and solids, right? These are things that we've been doing all semester long. Hopefully we've got that down. So remember that our delta G is equal to delta G naught, right, plus RT ln of Q. All right, well, Q for this reaction, products divided by reactants, we can mix aqueous things and gases together in an overall Q or K. So I can write this as zinc 2 times the partial pressure of our hydrogen divided by zinc, nope, that's a solid, we don't want to include it, times, or divided by our H plus concentration, and we've got to put that in as squared. So once we solve for this, right, this is going to end up being that delta G would be equal to delta G naught plus, all right, our RT times the natural log of all of this stuff, right? We'd have to plug all those values in. And we plug in the correct R, right? Our 8.3145 times 10 to the minus third kilojoules per Kelvin. We'd have to plug in the temperature, and we might need our standard Gibbs free energy from somewhere, right? But that's all we're doing is we're going to use that to plug in for our reaction quotient. That may change the spontaneity. All right, we can see this entire thing in practice by working sample problem 20-6. So this says for the reaction, all right, oxygen plus 4 acids plus 4 iron 2s and so on. We want to calculate our delta G at 25 degrees Celsius. All right, notice that, right, because our delta G is at 25 degrees Celsius, I can use products minus reactants, right, only at 25 degrees Celsius. Right, if it was at any other temperature, delta G is equal to delta H minus T delta S, right? But at 25, we can do products minus reactants. So if I wanted to calculate this out, right, my delta G would be equal to, all right, I have 2 moles of water. I'm going to write this out one time here so we can double check how we do these things. Again, right, you're going to do these several times again, so if you get confused, I'm going to look this up and I say, okay, negative 237.2 kilojoules per mole plus 4 moles of iron 3, and they are each negative 4.4 kilojoules per mole. All right, I'm going to take all of that and I'm going to subtract off my reactants. I got 1 mole of oxygen. That is an element. And for delta G and delta H, elements are 0. All right, we're going to add to that. All right, I'm running out of space over there, so we're going to add to that on the down here. We now have, all right, 4 moles of H plus. All right, if I look that up, it is also 0 kilojoules per mole. Delta G and delta H, strong acid is 0 kilojoules per mole. All right, plus 4 moles of our iron 2. All right, so iron 2 happens to be negative 78.9 kilojoules per mole. So our delta G for this, as we calculate it through, is negative 177.6 kilojoules. All right, part B, right, wants me to calculate delta G at 25 degrees Celsius when iron 2 and iron 3 are both 0.25 molar, and the partial pressure of oxygen is 0.755, and the pH is 3.12. All right, so if we find the H plus concentration, that'll give us everything that we need to plug in for our Q value. So let's start by finding our H plus, right? Same thing that we would do in the acid-base chapter. Our H plus is equal to 10 to the minus pH, which is 10 to the minus 3.12, and that gives us 7.6 times 10 to the minus 4th molarity. All right, now I could plug everything in to our delta G equation down here, but I'm just going to do this in a couple steps just so I can show you that we're going to do the Q, and then I'll just plug that Q value in to that overall equation next. So our Q then is our iron 3 concentration. So if we look back to the problem, right, our iron 3 concentration was 0.250, and we've got to raise that to the 4th power, divided by the partial pressure of our oxygen, right? And the partial pressure of our oxygen was said to be 0.755. And then we've got our H plus concentration that we just found, 7.6 times 10 to the minus 4th, which we have to raise to the 4th power. And then iron 2, which was 0.250, also raised to the 4th power. And so our Q for this is going to be 3.97 times 10 to the 12th. Now we're going to plug that in down here. So our delta G is equal to the delta G naught that we found as negative 177.6 kilojoules plus, all right, 8.3145 times 10 to the minus 3rd kilojoules per Kelvin. Our temperature is at 25 degrees Celsius, so 298 Kelvin, right? Remember, we got to have Kelvin, times the natural log of, all right, 3.97 times 10 to the 12th. I find sometimes doing the Q first makes it just a little bit easier. It's just less stuff to have to be plugging into your calculator with, parentheses and stuff over there in the Q, which is why I kind of did it that way to begin with. So our delta G is now negative 105.6 kilojoules. All right, now it didn't change the spontaneity. We went from negative 177.6 to negative 105.6. They're both negative. They're both spontaneous, right? But we're inching our way closer and closer towards that because we did change our overall concentrations there. Well, we saw in our previous sample problem that changing the concentrations or pressures of gases and aqueous solutions can cause our Q to change. And that can actually lead to changing whether a reaction is spontaneous or not. Now, it didn't in our sample problem, but let's look here where I have ammonium chloride, NH4Cl, which is a solid, decomposing into ammonia and hydrogen chloride gas. All right, so this reaction at 300 degrees Celsius, right, and we've given that the delta G naught, so at standard conditions, right, so this means that the pressures of those two gases are both 1 atmosphere. Our delta G naught is equal to positive 13 kilojoules, which is a non-spontaneous reaction. Now, if we change the pressures for both the ammonia and the HCl to 0.1 atmosphere, why don't we see what's going to happen? So when we have that situation, right, now we're going to calculate a Gibbs free energy that is not at standard conditions. And we do that by saying that the Gibbs free energy at non-standard conditions is equal to the standard Gibbs free energy plus our RT ln of our Q. So let's plug in what we know. We're looking for our delta G, our new delta G, is equal to 13 kilojoules plus our R, 8.3145 times 10 to the minus third kilojoules per Kelvin, times our temperature. Our temperature is 300 degrees Celsius, and so we need to convert that into Kelvin. So 573 Kelvin times the natural log of Q. All right, our Q is products divided by reactants. So that's the partial pressure of ammonia times the partial pressure of our hydrogen chloride gas. And each one of those are 0.1 atmospheres. So 0.1 times 0.1 is 0.1 squared. All right, we work through this mathematically, and we're going to get that our delta G for this is now negative 8.9 kilojoules. All right, so now this is spontaneous. By changing the pressures of those gases, or we could change the concentrations of aqueous solutions, we have actually changed, in this case, something that was non-spontaneous at 300 degrees Celsius into a reaction that is spontaneous at 300 degrees Celsius. From the previous few slides, we have noticed that there is a relationship, right, between our Gibbs free energy, right, which is also a relationship between whether or not our reaction is spontaneous or not, and the concentrations or pressures of our reactants and products. And we showed that with the equation that our delta G is equal to delta G naught plus RT ln of Q. All right, another thing that we should know by now is that when we are at equilibria, right? Number one, when we're at equilibria, something that we learned all the way back in chapter 17 and that we're going to keep talking about. When we're at equilibria, then our reaction quotient Q is equal to our K, right? Because K is at equilibria, so if Q equals K, then by definition we have to be at equilibria as well. And earlier in this chapter we learned that if our Gibbs free energy is 0, then we're at equilibria. Because if it's negative, then we're spontaneous. If it's positive, we're non-spontaneous. So in between those, we got to be at 0. That is when we are at equilibria. So if we know those two things, we can plug them into our top equation. And we can say, okay, if I'm at equilibria, instead of having Q, let's make that K. Right? And if I'm at equilibria, instead of us solving for a delta G, we know that we're at equilibria, so let's call that 0. Now let's rearrange that equation. All right, we have 0 is equal to delta G naught plus RT ln of K. If I rearrange that and solve for my Gibbs free energy change, right, at standard conditions, that is equal to negative RT ln of K. So now there's a relationship between our standard Gibbs free energy and our equilibria constant. Okay, we're going to take the information that we learned that our delta G naught is equal to negative RT ln of K, and we're going to expand upon that into something that's a little bit more of a complicated problem. It's just got a couple extra steps at the end. The basics are still the same, but we do have a little bit that we're going to expand upon at the end. So this says carbon monoxide poisoning results when carbon monoxide replaces oxygen in our blood. All right, now I'm going to shorthand this because hemoglobin's a huge molecule and I don't want to write it out. So hemoglobin I'm shorthanding as HB, and when it's with oxygen, it's HB.O2. When it's with carbon monoxide, it's HB.CO. All right, I give the equilibrium equation there, and it says that at 37 degrees Celsius, the standard Gibbs free energy for this is about negative 14 kilojoules. I want to know the ratio of oxygen blood to carbon monoxide blood when the pressure of CO is the same as O2. So there's a couple little tricks here. All right, number one, right, we've got our delta G is equal to our negative RT ln of K. So that is also negative 14 is equal to negative RT ln of K. So I can plug stuff in here and I can say, okay, I have negative 14 kilojoules is equal to negative 8.3145 times 10 to the minus third kilojoules per Kelvin, right? Remember, we got to use the right R, times our temperature, which is 37 degrees Celsius, or 310 Kelvin. We've got to get in Kelvin. And then I'm going to do the natural log of my K. All right, I'm going to move some stuff around algebraically, and I get 5.43 is equal to the natural log of K. All right, please note that this number, this 5.43, is rounded. Do not round in your calculator. Use whatever value they put in there. Whenever you're doing the natural logs of stuff and then you've got to get rid of that by doing e to the whatever, if you round at all, it can get off by huge factors. So do not round that in your own calculator. I just rounded it out because I don't want to write out every single stupid number that was given to me. Just keep it in your calculator, and you can round things at the very end of your problem, but never round before that. So if I do this, if I take e to the both sides, then I'm going to get that K is equal to 229. All right, what is K? All right, well, K is products divided by reactants. So my products are the concentration of the carbonated blood, right, or the carbon monoxide blood, sorry, times the partial pressure of O2 divided by the oxygenated hemoglobin times the partial pressure of carbon monoxide. All right, the problem tells us that the pressure of CO is the same as that of O2. So no matter what those values are, they're going to cancel each other out. So K is the ratio of CO blood to oxygenated blood. All right, but I want the ratio of oxygenated blood to carbon monoxide blood. So what I really need is the inverse of K. So 1 over 229 is equal to 0.4, oops, way smaller than that, 0.0044. All right, so what that tells us is that for every one, right, particle of blood in our system that has oxygen, there are going to be 229 of them that are going to have carbon monoxide. So if you go into a room that has the same amount of carbon monoxide and the same amount of oxygen in it, and you start breathing it in, your blood is going to fill up with carbon monoxide in it and almost no oxygen, right? 1 to every 229, which your body can't use the carbon monoxide, which will suffocate you. So let's not do that, everyone. All right, so our next podcast, and our very last one for this chapter, is going to go over what happens when we couple reactions together. How do we manipulate that with our delta Gs?